In this video tutorial, we will discuss the topics of limiting reagents and percentage yield. So in our last video, we saw how stoichiometric ratios can be used to describe the quantitative relationship between different substances, typically in a chemical reaction. And so long as you have information about one substance, you can use the original stoichiometric ratios to predict the quantities involved with the other substances. Because the original ratio was 1:1, 3 cows is enough to make 3 burgers. While the ratio between cows and buns was a 1:2, so twice as many, well, twice as many cows requires twice as many buns, in this case 6. Where we ran into problem was when we tried to apply these mass ratios, because 6 plus 3 grams does not add up to 3 grams. So if we can't take the direct route, we need to take a little detour into the land of the mole. Now we can tunnel through to the other side using our ratios and convert the mole value back into a mass value. Alright, so far so good. Now up until this point, we've been dealing with single scenarios, where if I have 4 cows, how many burgers can I make? Well, because it's a 1:1 ratio, I can make 4 burgers. But what if I had 6 buns and 4 cows? Now how many burgers can I make? Well, I still have enough cows to make 4 burgers, but I only have enough buns to make 3 burgers. So how many burgers can I actually make? The cows are telling me I can make 4, but the buns are telling me I can make 3. Which one is correct? Who's telling me the truth? And who's lying? I'm pretty sure most of you get this, but let's look at it visually over here. I have 6 buns and 4 cows. Although I have enough cows to make 4 burgers, I will run out of buns first. So in actuality, I only have enough ingredients to create 3 burgers and 1 steak. So here we call the buns the limiting reagent. This limits the reaction. This ingredient limits how many I can actually make. While the cows are called the excess reagent, because once the reaction's over, we will have leftover cows in excess. So in the end, the limiting reagent determines how many products can actually be created, while the excess reagent is just wishful thinking. So when you're trying to determine how much you can create, only trust the limiting reagent, do not trust the excess reagent. Now these types of problems are called limiting reagent problems, because you will be given starting values for each reactant, but you won't know which one is going to run out first. And these limiting reagent problems are essentially simple stoichiometry problems, but done twice. We first use stoichiometry to determine, using this many reactants, how many products can it create. Then using this many reactants, how many products can it create. You then compare the 2 values, and the one that is lower is the limiting reagent. The other one is excess, and you can generally just ignore that one. Alright, let's try out the sample problem over here. First step, write out the chemical equation. Alright, so by now you should know how to do nomenclature. Aluminum hydroxide, AlOH3. Hydrogen bromide, HBr. By now you should also be able to predict the products of these chemical reactions. In this case, it's a double displacement reaction. In this case, you'll produce aluminum bromide and H2O. Now the next step is very important. Balance it. If you do not balance the equation, you can't find your stoichiometric ratios. Without those ratios, you can't do stoichiometry. So the ratio is 1:3, 1:3. Now here's what I like to do next. I like to place the information directly underneath the chemical compound. So 15 grams of aluminum hydroxide, 15 grams of aluminum hydroxide. 20 grams of hydrogen bromide, 20 grams of hydrogen bromide. I find this helps to keep my information organized. Now since it's asking what mass of water is being produced, I'm going to try and find out how many grams of water can be produced with 20 grams of HBr, and how many grams of water can be produced with 15 grams of aluminum hydroxide. I can then compare these 2 values, and whichever one's lower is my limiting reagent. And that would be the number I would trust to calculate the mass of water that is going to be produced. Now, as we saw before, we can't just go directly through our ratios because the mass ratios don't make sense, which means we'll need to take a detour into the land of the mole. If you recall, mole is equal to mass divided by molar mass. So the mass of the aluminum hydroxide is 15 grams. Molar mass of aluminum hydroxide is 78.01 grams per mole. I can find this, of course, from the periodic table. Divide that out, and I get 0.19228 ... moles of aluminum hydroxide. Now please remember, don't try to round these numbers yet. Only round your final answer. Don't try to round inside the actual calculations, otherwise the error will be magnified throughout. But as I mentioned before, usually 4, 5, or 6 significant figures is good enough for you. I'm going to do the exact same thing for the hydrogen bromide. mass is 20 grams, molar mass of HBr is 80.91 grams per mole. Now be careful, do not factor in this coefficient when calculating the molar mass. You will factor in this coefficient when you do the ratios. But if you do it at the ratios and also the molar mass, you end up tripling your value, and that's not going to give you the right answer. Alright, so right now this is moles of hydrogen bromide and moles of aluminum hydroxide, so I need to convert them into moles of water. And we can do this by using our ratios, 3 to 3. Now, for simple ratios like this, 3 to 3, most students don't really need to calculate it. They already know it's going to be the same value. But if you have an ugly ratio, like, I don't know, 13 to 3, it would be a lot more difficult to calculate this ratio in your head. So if your algebra skills aren't that great, here's a little shortcut you can do. Take your number, the moles of whatever you're trying to convert, and divide it by its coefficient. Then multiply it by the coefficient of where you want to convert it to. Okay, so divide by where you are, and then multiply by where you're going. And that will essentially give you the right number. Now in this case, you would just divide by 3, but then multiply by 3. So you get the same number anyway. With this one over here, you would take 0.19228 and divide it by the coefficient here. Since there's no coefficient shown, you may assume it's a 1. So 0.19228 divided by 1, and then multiply by the coefficient of where you're going. In this case, a 3. So essentially, it's just 3 times as much. And that would give you 0.57684 moles of water. So now we can compare these two values to find out who is the limiting reagent. Remember, the one with the greater amount is overestimating, that is your excess reagent, while the one with the smaller amount is your limiting reagent, and that'll tell you how much you can actually make before you start running out of other reactants. So in this case, the aluminum hydroxide will be your excess reagent, while HBr is your limiting reagent. Although you have enough aluminum hydroxide to produce this much water, you will run out of HBr long before you can even reach this point. So we can ignore this value and continue on with the limiting reagent value. Since the question asks for how many grams of water will be produced, we got to convert it back to a mass. So notice how we're using mole of water, and we have to use molar mass of water. Alright, so don't mix and match, don't use the molar mass of HBr, because now we're talking about trying to find the mass of water. This is why I like to organize my calculations visually like this, to keep things separate. Anyway, again, don't factor in the coefficient in your calculation of the molar mass. 18.02 is just one water molecule. That's all you need. The 3 over here has already been factored in during the ratio calculations. There's no need to refactor them in again. Anyway, multiply the mole value by the molar mass and you get 4.45 grams of water actually being produced. Now, it's important to note that you can't determine who is your limiting reagent just by looking at the initial values. So you can't just say, oh, there's 15 grams, so there's less mass of aluminum hydroxide, therefore this must be my limiting reagent, because as you saw over here, the 15 grams was actually in excess. And that's because different compounds have different molar mass values. Furthermore, you can't just look at the mole values initially and say, oh, there's less moles of aluminum hydroxide, therefore the aluminum hydroxide must be my limiting reagent. Again, that's not true. It turned out it was in excess because you need to factor in the ratios afterwards as well. So for every 1 aluminum hydroxide, you can create 3 times as many waters, whereas HBr is a 1-to-1 ratio. Alright, so the only way to determine who is your limiting reagent is to convert, do your ratios, and find out how many moles of product you can create here. Do the same thing, convert to moles, do your ratios, find out how many moles of product you can create here, and compare these two values. Just make sure you're comparing to the same chemical compound. So you can't compare HBr to water and then with aluminum hydroxide compare to AlBr3 instead. You must compare apples to apples, not apples to oranges. Alright, let's try this sample question over here. You'll notice the coefficients are going to be ugly this time. So this will test your ability to do your stoichiometric ratios. But essentially I have 35 grams of FeS2, 25 grams of oxygen, and I want to know how many grams of SO2 will I actually produce. So you don't know who is going to run out first. Alright, so pause the video. When you're ready, press play, and we'll take this up together. Alright, so the first step, convert these masses into their mole values. Mole is equal to mass divided by the molar mass, 35 grams, molar mass of FeS2, 119.99 grams per mole. We can get this from the periodic table. Just remember, don't multiply by the 4. That's not necessary. This will be factored in once you do your ratios. Over here we have 25 grams. Molar mass of oxygen is 32 grams per mole. divide those two numbers, 0.78125 moles of oxygen. Now, me personally, I like to block off these values because I know they're going to be important and I'm going to be using them later on in my calculations. It makes it a lot easier for me to identify instead of having to search for these numbers later on. All right, now we do our ratios. You'll notice that this ratio over here is pretty simple to do, 4 to 8. So you're just going to double this number. But if you're struggling with the ratios, here's the shortcut. Divide by where you are, then multiply by where you're going. So in this case, 0.29169 divided by 4, and then multiply by 8. And that will give you 0.58338 moles of sulfur dioxide. Now this ratio is a little more interesting. Most students can do this one in their heads, but if you can do this one in your head, 11/8 of 0.78125 moles, you are mathematically gifted. You should be performing with Cirque du Soleil. But for the rest of us, do the shortcut, 0.78125, divided by where I am, so divide by 11, multiply by where I'm going, so multiply by 8, and you'll end up with 0.56818 moles of SO2. All right, so they're both very, very close, but this one is the one that's going to be my limiting reagent. It started off with a lower mass number, but then it had a larger number of moles, and then finally ended up with the least amount of moles of SO2 once you did your conversion factors. All right, so you can never predict the limiting reagent just by looking at this side. It has to be compared on this side. All right, so we have the limiting reagent and we now have the excess reagent. So using this value, mass is mole times molar mass. Make sure you're using the molar mass of SO2. Do not use this 8. Multiply by the 0.56818 and we get 36.40 grams of sulfur dioxide. Now, of course, we're only supposed to have 3 sig figs, so I'll just drop that extra 0 there. Now, another type of problem you might encounter in these situations is the question may say, well, after the reaction is over, how much of the excess reagent do you have left over sitting inside your beaker? So how much of the excess reagent did not react with the limiting reagent? So let's go back to this simple example over here. We know the cows are your excess reagent, but how many cows are left over when the buns run out? Well, when I draw it out, it's quite obvious. There's 1 cow left over, but there's no way you're going to be able to draw this one out. So how do we know there was 1 cow left? Well, now that you know who the limiting reagent is, you don't really need these values over here. You don't need to focus on burgers anymore. Let's focus on the cows, the excess reagent. So what I'm going to do is use my ratios from the limiting reagent to the excess reagent, and I know it's a 2-to-1 ratio between them. And in so doing, I have calculated how many cows were used up. So 2 buns are used for every 1 cow, so 2-to-1 ratio, so 6 buns used up 3 cows, which you can see visualized over here. So if I had 4 cows originally and 3 cows were used up, I can just subtract these two and I get 1 cow left. Well, let's apply that situation here. Now that I know who the limiting reagent is, I can ignore the product because I'm not going to focus on that. I'm going to focus on the excess reagent and how much is left over. So the first step was to take your limiting reagent, use your ratios to find out how many of the excess was used up. So I'll take my limiting reagent, use the ratios to find out how much of the excess was used up. This ratio is a 3-to-1. So divide by where you are, so divide by 3, multiply by where you're going. In this case, it's a 1. So divide by 3, multiply by 1, and you get 0.082397 moles of aluminum hydroxide used up. We then subtract this value from how much was originally there, and that'll tell you how much is left over. So here's how much was originally there. Here's how much was used up. Subtract the two values, and we have 0.10988 moles of aluminum hydroxide left. And if the question asks for it, you can convert this value into a mass. So mass is mole times molar mass. You've got the mole value. You've got the molar mass of aluminum hydroxide, multiplied by the 2, and 8.57 grams of aluminum hydroxide is left over after this reaction is finished. All right, so the last topic we want to look at is called percentage yield. This describes how successfully a reaction converts reactants into products. So you would take the actual amount of product that was produced during the experiment, so sometimes they'll call this the experimental amount produced, and then divide it by the theoretical amount that could have been produced if everything went perfectly. Divide these two, multiply by 100%, and you get your percent yield. So this is like saying, what percentage do you get on the test? Well, you take your actual score, divide by the theoretical score that you could have gotten if everything went perfectly. So what's the maximum value you could have gotten? Then multiply by 100%. Now, there are several reasons why you should never get 100% yield. If you ever do get 100% yield, I'd be very concerned. Chances are you probably have some sort of an impurity inside your sample, which accounts for the extra mass. But here are the major reasons why 100% yield is unlikely. The first is experimental error. This is the major one. When you transfer a chemical from one beaker to another, can you guarantee that every single atom that was in this beaker was transferred to the other one? No. So how can you get exactly 4.45 grams if some of the reactants were lost during the actual experiment? Now, this is just one aspect, one example. There's so many different ways where you could lose product or not be able to collect it all, like during filtration. Now, the second reason why you won't get 100% yield is due to impure reactants. So when you buy a chemical from a manufacturer, they can't guarantee that every single atom inside that bottle is what you purchased. There will always be some sort of impurities. So typically these labels on the back will say, oh, it's 99.9% pure. Or if you really want the cheap stuff that I use for my grade 9s, it'll just say 95% pure. But you will never see the manufacturer state that it's 100% pure because they can't guarantee that. So when I scoop out 15 grams of aluminum hydroxide, I can't guarantee that exactly 15.0 grams of that powder is exactly aluminum hydroxide. More than likely, part of this mass contains a contaminant or an impurity. So again, there's no way you can get exactly 4.45 grams of your final product. Now the final reason is due to competing reactions. So let's take a look at this reaction over here. Phosphorus plus chlorine produces phosphorus trichloride. Now I know this reaction is not balanced, but let's just ignore that for a second. The problem with this reaction is that the product over here, phosphorus trichloride, can then react with the initial reactants, chlorine, to produce PCl5. We call this a side reaction or a competing reaction because it competes with what I originally wanted. So let's take a look at this beaker over here. Theoretically, I have enough reactants to produce 1, 2, 3, 4, 5 of these PCl3 molecules. So if everything went perfectly, that's how many I should get. Well, let's start combining them. Phosphorus plus chlorine turns into PCl3. And this phosphorus and this chlorine should also turn into a PCl3. But there's that side reaction where PCl3 can react with chlorine to make PCl5, which is a product that I don't want. So now there's a chance, an opportunity for this PCl3 to react with this Cl2, creating PCl5. And now I've got a sad phosphorus by itself with no partner to make PCl3. And now the best case scenario, instead of making 5 PCl3s, I can only potentially make 3 PCl3s now. Although more than likely, I'll probably make more of the unwanted PCl5. So competing reactions prevent you from making the amount that you wanted to make, that you could have made. Alright, so reasons why we shouldn't get 100% yield: experimental error, impure reactants, and competing reactions. Alright, so looking back at this equation, the numerator is the value we get from our experiment. So you do the experiment, you actually measure this mass, you measure this amount. That is how you obtain this value. To obtain this value over here, you would do your stoichiometry calculations. Because in the mathematical world, it assumes everything goes perfectly. So this is the maximum amount you can make. It doesn't worry about purity or experimental errors or competing reactions. It's just straightforward mathematics. How much can I make if everything reacts according to plan? Alright, so let's pretend this reaction has a 72% yield. It's only 72% successful. Well, how much of the water will you actually make in the experiment then? Well, let's take a look at the equation. So the percent yield is equal to how much you can actually create divided by how much could have been created times 100%. So when I substitute these values in, 72%, 72%, 4.45 grams is how much I could have made theoretically if everything went perfect, and then 100%, I'm going to solve for actual. To get rid of this 100%, I'm going to divide on this side, so 72 out of 100 gives you 0.72. I'm going to multiply out the 4.45 and bring it up here, so 0.72 times 4.45 grams, and then you get a 3.2 gram of actual yield. So in the experiment, if I conducted this reaction over here, and this reaction is only 72% successful, I start off with 15 grams and 20 grams of this, I theoretically, not theoretically, actually in a lab, should be able to get about 3.2 grams overall out of the possible 4.45 grams that I could have gotten if everything went perfectly. Now here is another example of a different type of percent yield calculation. Instead of going forwards telling me how much I'm going to make, let's go backwards to see what amount do I need to make this value. So let's pretend this reaction has a 91% yield, and I want to make exactly 18 grams of sodium chloride. So I want to actually collect this mass of sodium chloride, not theoretically get it. I want to actually recuperate 18 grams after factoring this 91%. So if this reaction is only 91% successful, then I know if I aim for 18 grams, I'm going to end up with less than 18 grams. So what I need to do is aim higher so that when the 91% success rate comes through, I end up dropping to the value that I want. So the question is, how much sodium hydroxide do I need to overestimate the value theoretically I should get so that I end up with an actual value that I do want, 18 grams? Well, let's first plug in our values. It's a 91% yield. I'm going to get rid of this 100%, turning this into a 0.910. I want to actually produce 18 grams, so I'm going to write it over here. Now I can calculate how much I need to aim for in order to achieve 18 grams. So I'm going to multiply these out and bring them to switch places. And now I can divide the two, giving me 19.78 grams. So now I know I need to aim for 19.78 grams, so that after the 91% success rate, I end up with 18 grams, which is what I really wanted. And now we do our stoichiometric calculation. So I've got the mass, I've got the molar mass of NaCl, 58.44, divide mass by molar mass, and you get moles of NaCl. Don't forget to balance the equation. In this case, it's already balanced 1 to 1 to 1 to 1. So if it's a 1-to-1 ratio, 0.3385 moles of NaCl becomes 0.3385 moles of sodium hydroxide. Mass is equal to mole times molar mass of NaOH we can find from the periodic table, moles of NaOH we got from the ratios, multiply the two and you get 13.5 grams of sodium hydroxide is required so that after the 91% success rate, I end up with 18 grams, which is what I actually wanted to have. So you had to overestimate to get the amount that you wanted to have in the end. All right, and that is stoichiometry.